Yeah, so it has started recording. So welcome back to the last class of this course. So today we will do Minkowski's bound and as a corollary Hermit's theorem, and that will be the end of the course. And I've already told you in the last class what the NSEM assignment is, and you can do it whenever you have time. But before the actual, the deadline is the actual NSEM date. Yeah. Okay, let me start sharing the screen.
Sir?
Yeah.
What is the deadline?
Whenever is the NSEM that day.
Yes.
So if you have further questions on that, we can discuss after the lecture because this is being recorded. Yeah. But I am okay. If you are okay, you can ask. But otherwise, you can wait for the recording to be over. So today is. You can also ask me on WhatsApp if you have doubts. Yeah. Can you just confirm that you can see the slides?
We can see it.
Yeah. So today's keywords Minkowski and Hermit. So let us get to the lecture. So welcome to the last lecture of this course. Today we will do Minkowski's bound and also Hermit's theorem. Okay. So Hermann Minkowski was a German mathematician, 64 to 1909, and Charles Hermit was a French mathematician, 1822 to 1901. Okay, let's get started. So this is a setup. As a corollary to Minkowski's bound, finiteness of class group will also follow. There's a slightly easier proof which we skipped, or maybe in one of those extra classes we discussed. But since anyway this proof was coming, I did not put that in the slides. Okay, so K over Q is a number field, degree n. N we write as R1 plus 2R2, where R1 is the number of real embeddings and 2R2 is the number of complex embeddings. Complex embeddings come in pairs, so it's always an even number, which we write as 2R2. And A is an ideal in the ring of integers. OK is the ring of integers and A is an ideal. And we will, as usual, view A as a lattice in Rn. And last class we saw the following, that if you consider this region summation over the Archimedean absolute values. So how many Archimedean absolute values are there? R1 plus R2, right? Among the 2R2 complex embeddings, all of them will come in pairs and something and its conjugate will determine the same absolute value. So R1 plus R2 many absolute values. Archimedean absolute values, and NV is 1 if it's a real embedding and 2 if it's a complex embedding. So summation NV mod ZV less than or equal to A. This convex region, what was the volume? So this is what we computed using integrals and some change of variables. And we precisely know what the volume is. This we did last time. We also did last time, this was much easier, that the volume of a fundamental domain of A, you fix a fundamental domain of A, and its volume is given in terms of discriminant like this, 2 power minus R2 norm of A times square root of modulus of discriminant. These two we did last time, and remember dk is the discriminant of OK, and it's the absolute value of the discriminant that comes into all these things. Okay. So now you choose A, we are going to do Minkowski's bound. So this A you are going to choose. You remember in the last class we did three things. One was this and the other was this, and one more thing we did which is also due to Minkowski. In fact, the Minkowski is the key name in this chapter. This is what is called geometry of numbers. Geometry of numbers, because you are doing some volume computation and then existence of lattice points. So Minkowski's result, I did not attribute it to Minkowski, but it is due to Minkowski, is that if you have a region which is closed, convex, and symmetric, and if its volume is sufficiently large, in fact 2 power n times volume of a fundamental domain, bigger than that, then it contains at least one non-zero lattice point. We are going to use that now. Okay, so we will choose this A large enough so that that inequality is satisfied. So choose A so that A power n is this much. Okay, so this depends only on this depends on A and K, and you choose your small a such that A power n is this much, and that is chosen in such a way that because of these two results, this has this much volume and volume of a fundamental domain is this. Because of these two things, A is chosen so that volume of A is 2 power n volume of F. And the result of Minkowski was that if volume of A is bigger than or equal to 2 power n volume of F, then A has a lattice point. So last time we also saw this theorem on the existence of a non-zero lattice point in a closed convex symmetric subset C of Rn, provided volume of C is bigger than or equal to 2 power n volume of F. So we can apply this to A. You choose A big enough so that this is satisfied, and now you know that such an A has a lattice point. Our lattice is A, the ideal A. So there is an alpha which is non-zero belonging to A, belonging to this set capital A. But what is capital A? Capital A is summation NV mod ZV less than or equal to A. But what are ZVs? ZVs are the conjugates of Z. So for this alpha, alpha belongs to this. So various alpha V's, alpha subscript V, which is same as saying sigma alpha, as sigma is in the Galois element, and NV is 1 or 2 depending on real or complex, and all that put together, you can say that sigma 1 alpha plus etc. sigma n alpha modulus is less than or equal to E. Right? These are the embeddings. These are the sigma i's are the embeddings of K into C complex numbers, and some of them are R1 many are real embeddings, and 2 R2 many are remaining, and we are writing both of that, modulus is same, so that will give NV equal to 2. Okay, so this is exactly that region, and we know that there is a lattice point in that region. So indeed, this is because N1 plus R1 plus 2 R2 is N, and S infinity is R1 plus R2. So we are writing twice. Sigma I and its conjugate both are written here. So sum is twice something. And NV is 1 or 2, depending on the embedding is real or complex. Okay, so this is what we have got. Now we are going to use geometric mean is less than or equal to arithmetic mean for this thing. So arithmetic mean of these many things will be this divided by capital N. And what will be the geometric mean of this? Geometric mean of this is sigma 1 alpha times sigma n alpha power 1 by n. Modulus of this. Okay. So modulus of this times modulus of this times modulus of sigma n alpha. That is nothing but modulus of product of sigma I alpha, which is nothing but norm of alpha. So modulus of norm of alpha power 1 by n. So this is the geometric mean and this is the arithmetic mean. So this we have, and this is less than or equal to A. So this is less than or equal to A by N. In other words, norm of alpha modulus is less than or equal to raised to the power N. So A power N by N power N, which is N power N by N power N times this. Right? A power N, we chose A so that A power N is the numerator here. A power N is this one, N factorial times this much. Okay, so that's exactly this. So since alpha belongs to A, we know that alpha belongs to A, so the ideal generated by alpha is contained in A. And because you are in a Dedekind domain, you know that A divides alpha. If A contains alpha, then A divides alpha because you are in a Dedekind domain. And that means there exists an ideal B such that the product is this ideal alpha for some ideal B. Okay. Therefore, norm of alpha norm is multiplicative. Norm of this ideal, when you have principal ideal, norm of the ideal is same as the field norm of alpha and the ideal generated by that. So norm of this ideal is nothing but norm of this element alpha, and that is equal to norm of A times norm of B, which I am not putting modulus because the ideal norm is anyway positive. It's a cardinality, so it's positive. So modulus of norm of alpha is norm of A times norm of B. And if you plug in that here and cancel this norm of A on both sides, you will get norm of B less than or equal to n factorial by n power n 4 power r2 by pi power r2 times root of mod dk. This na is cancelled. Okay, so this is what is called the Minkowski bound. So Lang calls this much the Minkowski bound, but let's call the whole thing Minkowski bound. Okay. So thus, what have we concluded? So finiteness of class group is immediate because what you have concluded is given an ideal A, I am showing that there exists an ideal B, but B times A is a principal ideal. That means B is equivalent to A inverse. So given an ideal A, there is an ideal B equivalent to A inverse whose norm is bounded by a constant which depends only on the field K and on nothing else. Okay, because n is the degree and R2 is a number of half the number of complex embeddings, D is the discriminant of K. So it depends only on K. And so if you give me an ideal, I am looking at its inverse, and in its equivalence class, I am getting a B whose norm is bounded. So this shows there are only finitely many equivalence classes. Why? Because if there are infinitely many equivalence classes, I will get infinitely many representatives B, but the norm cannot be bounded. No, norm of an infinitely many different things cannot be bounded because norm is an integer. Because norm is from K to Q. So norm belongs to Z and norm is an integer. And given any bound, you have finitely many prime numbers less than or equal to that. And ideal is product of and on a given prime number, there are only finitely many prime ideals above that. And an ideal is product of prime ideals. But you could ask, what if a prime ideal comes to higher and higher powers? But that is also not possible because norm is bounded. So, right, norm is bounded. So P power R, what will be its norm? Norm of P power R will be norm of P power R, and norm of P is 1 by Q. So 1 by Q power R. So, so anyway, R cannot be high, no, because it is right. Norm of a prime ideal is, these are the normalized norms, and norm of a prime ideal is 1 by Q. It is less than 1. So 1 by Q power, a high power is anyway becoming smaller and smaller. No, so I need to do a little bit more thing. So I'm saying that norm of D is bounded by this, and yeah, we know that there is so number of prime numbers which can come here less than or equal to this. That is finitely many, and given a prime number above that, there are only finitely many prime ideals. So these are all only the allowed ideals in B. These are only the allowed ideals in B. Okay, so there's a small confusion in my mind, but basically this is the idea. We will come back to it. By that time, if I don't clear it, I'll come back to it at the very end. Okay, let's proceed. So given an ideal A, there's an ideal B which is equivalent to A inverse, such that norm B is bounded by a constant depending only on K. So there are only finitely many, this is what I verbally said, only finitely many prime numbers bounded by a given constant. And they can only be finitely many prime ideals of OK lying above a given prime number. And so there are only finitely many ideals with bounded norms. Since a prime ideal has to appear with an order which is bounded in such an ideal, and this is where I'm a bit confused because I'm just worried whether the power I'm getting correct or not. We will come back to it. Okay, but basically this is the proof. Let's discuss at the very end. So number of equivalence classes is finite, and the class group is generated by the equivalence classes of those prime ideals of norm less than. So you are getting a precise bound, and this can be used in order to compute class numbers in some cases. For example, one important example Pradyumna did in the last class using this, where he showed that the class number is actually 1. Using this and some more things, of course. Okay, so finiteness of class group follows. And a corollary is that the discriminant, absolute value of the discriminant is strictly bigger than 1 if k not equal to q. And this is also easy because you have this bound. You have this bound for b, and this is bigger than or equal to 1. Why is norm b bigger than or equal to 1? Because why is it true? Why is norm b bigger than or equal to 1? Because B is an ideal, and it's an integral ideal. So norm of this will be an ideal in Z. So it's generated by an integer, and so a positive integer, and a norm of that is an integer. So it's at least 1. Okay. Yeah, so this is bigger than or equal to 1, and this implies you are getting a bound for dk. So dk is bigger than or equal to this taken to this side, and taking square, you get pi by 4 power 2r2 n power 2n by n factorial square, which is bigger than or equal to, I'm replacing 2r2 by a bigger number, which is capital N. Capital N is r1 plus 2r2, and I can do that because pi by 4 is less than 1. So pi by 4 is less than 1. So when I make the exponent bigger, it's a greater than or equal to. So you get this. And you can check that this sequence, if you call this AN, this sequence is monotonic increasing, and A2 is already bigger than 1. So all these things are bigger than 1, strictly bigger than 1 if K is not Q. If K is not Q, then N is at least 2. Capital N is at least 2. And capital N is at least 2, and therefore dk is bigger than 1. Yeah, so that clears my mind here. I don't need to write this line here. This is unnecessary because what this much is enough. So there are only finitely many prime numbers bounded by a given constant, and you know that there can be only finitely many prime ideals lying above a given prime number. So only these things can contribute to B, right? With whatever power is coming, because you are getting a B, and you are getting norm B is bounded. So inside B, yeah, norm B is an integer. Norm B is an integer. So that's enough to show that it will be a finite. Only finitely many such ideals can be there. Okay. So dk is bigger than 1. This we need for the next statement. And here itself you can conclude. So this also we discussed in one of the last classes, that there is no everywhere unramified extension. If you take any extension of Q, any proper extension of Q, there's at least one prime number which will ramify, because dk is strictly bigger than 1, and therefore it will have a prime divisor, and primes dividing discriminant will ramify. So everywhere unramified meaning each prime is unramified. That cannot happen. At least one prime number is ramified because discriminant is bigger than 1. So at least one prime number will divide it. Okay. Now there is what is called Stirling approximation. I don't know whether you have seen this. It comes when you look at gamma function and all that, and by which you can also get an approximation for n factorial, and I've just taken this from Lang, and I looked at the proof also on Wikipedia. It involves some gamma function and some basic stuff. Okay, so n factorial is equal to square root of 2 pi n by e power n e power theta by 12n for some theta between 0 and 1. Okay, so from this you get the famous bounds for n factorial. Okay, so by putting this into this inequality, you can substitute n factorial by this, and you will get something. Okay, you have put e now. Now if you take log mod dk, you can apply log on this, you will get something. Okay, so this 2n log with respect to e, so 2n you got from e square power n minus theta by 6n you got from here, minus log 2 pi n you got from here, and n log pi by 4 you got from here. Okay, now what you can observe is that this is bigger than or equal to some constant, some positive constant times n. You can find such a positive constant by doing the exact calculation here for an n. This is bigger than or equal to. So when n is large enough, it's easy, but n equal to 2 or something, maybe you have to actually plug in and see. Okay. In any case, you can get log mod dk is bigger than or equal to a positive constant times n. In other words, n by log dk is less than or equal to 1 by this, which is another constant. Okay, so this is what we saw last time. I mean, verbally we said that the degree n divided by log mod dk is bounded for k not equal to q. K not equal to q we are using because otherwise this is 0. Dk is 1. So we know that if k not equal to q, dk is strictly bigger than 1, and n by log dk is bounded. So the degree of k over q by log mod dk is bounded. So this follows. Okay, now we can come to Hermit's theorem. So some people call this result itself Hermit's theorem, but the corollary is what Lang calls Hermit's theorem. So this is the last result of our course. There are only finitely many number fields with a given value of the discriminant. If you give me a value, if you give me a number, an integer, then there are only finitely many number fields with that as the discriminant. So let's see the proof. First observation is this. So we already saw that the degree by log mod dk is bounded, and therefore the degree is bounded if the discriminant is bounded, right? This is less than or equal to an absolute constant. So degree is less than or equal to a constant times log mod dk. So if discriminant is bounded, then log mod discriminant is bounded times a constant that is bounded. So degree of k over q is bounded. Okay. So because of our Minkowski's bound, using that we showed that this is bounded, and it follows that if the discriminant is bounded, then the degree is bounded. And therefore, in order to show this without loss of generality, we need to show, suffices to show that there are only finitely many k. We need to show that there are only finitely many k with a given value of the discriminant. Okay, but you have already given me a value, and I have to show that that value only finitely many fields will have, and it's enough to show that there are only finitely many k with a given degree n and with a given value of the discriminant. Because if discriminant value is given to me, if discriminant is that, then the degree is bounded. So it's enough to show with a given degree. Okay, so this is a crucial reduction step. In order to show that there are only finitely many k with a given value of the discriminant, it is enough to show there are only finitely many k with bounded degree and with a given value of the discriminant. So that's what we are going to show now. So as usual, write r power n as product over the Archimedean absolute values, product over the completions, and assume there is at least one complex absolute value. This is only for notational purposes. If it's real, like one of these results that we proved last time, it's even easier. So we will just make that statement at the end. Assume that there is at least one complex absolute value, and consider the domain defined by, so I should put a pause here maybe. So modulus of zv0 minus z bar v0. So identify v0 with a complex plane. Okay. k v naught is identified with a complex plane, and there zv0 minus zv0 bar modulus is less than or equal to c1 root b. C1 is going to be a large enough constant, and the sum is less than or equal to half on that complex plane. For all other absolute values, the modulus is less than or equal to half. Take this domain. Now this domain is closed, convex and symmetric. And choosing C1 large enough, it has large enough volume. And we know from that geometric result that if your domain is closed, convex, symmetric, and if the volume is large enough, then lattice points are guaranteed. Depending on the lattice, this volume should be at least 2 power n times the volume of a fundamental domain of that lattice. And we are going to take the lattice to be OK, the ring itself. So we know by choosing C1 large enough, we know that there is a non-zero point in this domain, which is in OK. OK is our lattice. Okay, so you have got such an alpha. Now, norm alpha is bigger than or equal to 1 because alpha is an algebraic integer. Therefore, norm alpha is an integer, and therefore norm alpha is bigger than or equal to 1. Bigger than or equal to 1. And okay, because it's non-zero and it's an algebraic integer, and therefore from this inequalities, what can you conclude? See, norm is bigger than or equal to 1, but at all these completions, the norm is less than or equal to half. And at this point, the sum of the complex numbers, so the real part is less than 1, and the imaginary part can be bigger. So if norm is bigger than 1, then since the real part is less than half, less than 1 by 4 actually, because this is twice the real part, we can conclude that the imaginary part is bigger than 1. Because if real part is less than 1 and imaginary part is less than 1, then it's a real part is actually less than 1 by 4. And if imaginary part is small, then you will get the norm to be small, but norm is at least 1, and therefore you can conclude that the imaginary part is absolute value bigger than 1. Can we conclude bigger than 1? But anyway, I don't need it. I just want to say that imaginary part is non-zero, which is certainly true, because otherwise norm would have been less than 1 by 4. Okay, so in particular, the two conjugates of alpha corresponding to V0 are distinct, right? So alpha and alpha bar are distinct, because imaginary part is non-zero. Alpha bar is, if alpha is x plus iy, alpha bar is x minus iy, and y is non-zero. So these are two distinct points. So this you are concluding from something that I might have mentioned, but we did not put it on the slides, which is that if you have an extension of number fields and if you fix any place downstairs, then the norm is the product of local norms with W lying over V. That's what we are applying here with V to be V naught. So if you take V to be V naught, then there are two. Maybe we don't even need this. So I'm saying that, yeah, so the usual norm is related to the local norm. That's all that I'm saying. The usual norm is same as product of the local norms, but if you take a complex place, then it is exactly the complex norm. And from that only we concluded that the two conjugates are distinct. Okay, so here is a reference because I did not put this in the slides. And we can also conclude that for V not equal to V naught, the absolute value of alpha V is different from the absolute value of alpha V naught. Why is that? Again from these inequalities. Because we know that the absolute value of alpha V naught is bigger than 1, because norm alpha is bigger than 1. No, norm alpha is bigger than 1. We have used in order to show that yeah, in order to show that Yeah, sorry. So here also I should have stated carefully. I got confused. So how are we applying this remark? This remark we are applying for E as K and K as Q. So norm from K to Q, that's a global norm. That is what I have written here, the global norm. That is product over, here you take V to be infinity. So Q has only one Archimedean place. And W lying over V is all the Archimedean places. So W lying over V is same as saying W belonging to S infinity. All the Archimedean places. So at all the Archimedean places, if you take the local norm and if you take the product, that is this N alpha. Okay. Now if you come here, these are all the Archimedean norms. These are all the infinite norms, infinite absolute values. So the product of all these things together is norm alpha. But at V not equal to V naught, it is less than, the local norm is less than or equal to half. Okay. But here, so the product is bigger than 1 except at one place everywhere it's less than half. Product is bigger than 1. Therefore, at this place it has to be bigger than 1. And at this place, for it to be bigger than 1, the imaginary part has to be large enough. That's how we conclude it. And we can also conclude that mod alpha V is different from mod alpha V naught. Why? Because mod alpha V naught is bigger than 1 and mod alpha V is less than or equal to half. Therefore, mod alpha V is not mod alpha V naught for all V not equal to V naught. So that's the second observation. Alpha is distinct from, and this is from the inequalities. This is because alpha belongs to that region. And from this, it follows that alpha is distinct from any other conjugate. Right? Because any other conjugate, sigma is some other embedding, and on some other embedding already the absolute values are different, and therefore you conclude that alpha is not any other conjugate of it. And in this complex place V naught also, alpha and alpha bar are distinct. Okay, so from this what you can conclude is, alpha generates the field K over Q because it is distinct from all its conjugates. And at the complex place also, that and its bar are distinct, so there are enough linear independence you are getting out of alpha. Okay, so alpha generates the field K. And now we are almost done. Look at its minimal polynomial of alpha. Because alpha is an algebraic integer, it will have coefficients in Z, and the coefficients will be symmetric polynomials in alpha and its conjugates. And from that you can conclude, and alpha belongs to this region, all its conjugates also belong to that region, and we know that all of them are bounded. So this is our region, all of them are bounded, all these places by half, and otherwise C1 root D. C1 is a large constant depending only on n, and root D is coming, D is the absolute, D is the potential discriminant. D is finally the discriminant. Okay. D is a given number which we would like to be the discriminant. So this bound is a bound depending only on n and d. So alpha satisfies a polynomial whose coefficients are bounded in terms of d and n. It's a function of d and n. So alpha can satisfy only finitely many such polynomials, right? Because it is all the coefficients are bounded in terms of d and n, and polynomial has finitely many coefficients. So such polynomials, that collection is finite. So alpha can possibly satisfy only finitely many such polynomials. Therefore, there are only finitely many such k possible, because k is q alpha. Q alpha over q, as alpha varies, will give you all such number fields with degree bounded by n and discriminant the given d to be the discriminant. Okay, so there are only finitely many k with a given discriminant and a given degree. If there is no complex absolute value, same proof, instead of that the first two inequalities, you have just one inequality, C1 root D, C1 large enough, depending only on n. So the same proof goes through. Okay. So this is the main result. This is due to Hermit. So I was searching on the net because as you can see from the very first slide, Hermit did most of these things because before Minkowski's result. So the proof in Lang uses Minkowski's result, but this is not the original proof. Original proof of Hermit is different, something else using quadratic forms, etc. But this proof is better in the sense this is much more. I mean, anyway, Minkowski's results are nice results, and this proof is not the original proof of Hermit. Hermit had another proof. Okay, and what Lang calls Hermit's theorem is the following: for a finite set S of prime numbers, there are only finitely many number fields of bounded degree, meaning degree over Q, which are unramified outside S. So all the prime numbers outside S should be unramified in this extension. So the question is, you give me a finite set and you ask for number fields. All the degree, all of them should have degree less than or equal to a given number, and with the property that all the prime numbers outside this set S should be unramified. And the result is there are only finitely many such fields. Okay, and this is a very important result with a lot of applications. What is the proof? Proof is this is a corollary to the previous result that with a given discriminant there are only finitely many number fields. Okay, it's a corollary to that. How does it follow? Fix a prime number in S. It's a finite set of prime numbers, and consider QP, periodic numbers. Now, how many extensions does it have of bounded degree? This we had seen earlier, Krasner's lemma, application of Krasner's lemma, and application of characterizing totally ramified extensions in terms of Eisenstein polynomial and all those things. Chapter 2, we have seen that QP will have only finitely many extensions of a given degree or of bounded degree. Okay, so finitely many by Krasner, this is a reference. And because it's a finite set, if you consider the possible discriminants of all these extensions, so there are only finitely many extensions of bounded degree of QP. For each of that, you can compute the discriminant, and there are only a finite set. On that set, you take the maximum of the discriminant, because it's a finite set maximum you can take. So because of finiteness, their discriminants are bounded. It's a maximum of all those discriminants, so that's bounded. And we also know, we have seen it, that the global difference is a product of local difference. You know, this is a result which I skipped the proof, but I had stated it and used it. And we also know that the norm of different is a discriminant. So in other words, the global discriminant is product of local discriminant. Okay, you can have the local notion of discriminant and global as product of local. So if all the local discriminants are bounded, then the global discriminant is bounded. So the global discriminant is bounded. But then we know from the previous result that there are only finitely many extensions with a given discriminant. So if the possible discriminant is bounded, then there are only finitely many such extensions. We have seen that there are only finitely many number fields with a given value of the discriminant, and unramified outside S. What does that mean? That is same as saying only primes in S can possibly divide the discriminant. So all this put together, we are getting there are only finitely many such extensions. So if you give me a number, then and a finite set of prime numbers, then there are only finitely many number fields of degree less than or equal to that number, which have the property that primes outside S are certainly unramified. So it's a very beautiful result, and this is called Hermit's theorem. So this is the lecture part of this is the slide part of the lecture. So let's stop here, and we can discuss a little bit and then end the class. So maybe I'll stop the recording.